All right. To begin the process of simulating free particle moving across a potential barrier, we are to start with the energy of the potential barrier to be 0 electron volt, and then we are going to consider only the real part of the wave function, which is this, the real part of the wave function. Then we followed by the movement of the wave function. Thus, the wave movement start from the right to left. Then we are going to only consider a plane wave and then the sum at the start. Now, as we could all see, now the wave function signifies short wavelength. The wave function of the particle moving across the barrier is having a very short wavelength, having a very high energy. This is mathematically proven that the relationship between energy and wavelength is inversely proportionate. So by the time we increase the value of the potential barrier to a certain height, maybe close to that's at 0.5. Now the behavior of the wave function have changed. Then here in the potential well, the behavior of the particle is that it decays rapidly compared to the right hand side of the equation, thereby having a very minimal sinusoidal waveform at the right hand side of the well. When we increase a little bit further to be equal to the energy of the particle, now you could see that within the barrier, the amplitude outside at the right hand side of the barrier is very high. Then inside the barrier, there is an exponential decay of the wave function, and then having a very minimal sinusoidal waveform outside the barrier. This signifies that when the waveform when inside this signifies that the waveform the energy of the particle at the right hand side of the barrier is more than the energy of the particle at the left hand side of the barrier. Now, if we are to consider separate wave function, as we can see now, yes, inside the barrier we can see that there are two separate wave function. Outside, before at the right hand side there is separate wave function, inside also there is separate wave function. This is telling us that here one of the wave function exponentially decrease. When we move it the other way round, we could observe that when it is like this, now one of the wave function exponentially increase, which represents one part of the solution of a second order differential equation of time independent Schrodinger equation, which is exponential plus kx. Then here the exponential decay is now representing the other solution of second order derivatives of time independent Schrodinger equation, which is exponential minus kx. So far, so good. This is a little bit of what I am going to explain in relation to this. But in addition, you could see that the probability density inside the barrier signifies that the particle can only move within the barrier and outside the barrier there is no possibility of its decay, then when we reduce the energy of the particle, as we can see now, you can see that if we reduce the energy of the particle, we do observe a very large wavelength, meaning the energy of the particle is now decreasing while the wavelength keep increasing. So this is a little bit of what I know or what I can say about the simulation process of a free particle moving in a potential well. Thank you for listening.